Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Okay, let's unpack this. I want you to imagine, just for a second, that you are walking into a crowded room. You're at a party, maybe. You see your friends laughing over in the corner. You see the furniture, the walls, the snacks on the table.
Everything seems completely normal.
Exactly. It's the world you've known your entire life. But then someone hands you a special pair of glasses. Or maybe they just, lean in and whisper a secret in your ear.
And the secret is that you're practically blind.
Yes. The secret is that for every single person you can see in that room, there are 5 invisible ghosts standing right there next to them.
And not spooky ghosts.
No, not at all. I mean, massive, heavy, physical things.
Mm-hmm.
They are crowding the room. They're pushing things around. They are, in fact, holding the very walls of the room together.
Right.
If those invisible figures weren't there, the room would just explode. The furniture would fly off into space. Your friends would drift apart.
It is a slightly unsettling image when you put it that way.
It is.
But as an analogy, it is surprisingly accurate. That is essentially the state of cosmology right now. We are living in a room crowded with ghosts.
It's the ultimate invisibility paradox. We're sitting here, it's January 2026, and we're looking at a synthesis of the absolute latest research, the historical context, and the shifting paradigms in physics right now.
For sure.
And the headline, the thing that keeps physicists up at night, is this just mind-bending fact. 85% of the matter in the universe is completely invisible to us.
That's right, 85%.
We call it dark matter, which, frankly sounds very sci-fi and ominous. But the reality is, despite decades of searching, despite building the most sensitive machines in human history, we have never directly detected a single particle of it. Not one.
And I think it is so important to pause there and really appreciate the gravity of that statement. Pun definitely intended.
Yeah.
We aren't talking about a small rounding error in our calculations. We're not talking about, a decimal point out of place.
Yeah.
We are talking about the vast majority of the stuff that makes up reality. Think about everything you have ever seen or touched or measured.
Every star, every planet.
Every star in the sky, every planet, every mountain, every atom in your body, the air you are breathing right now, all of that.
Yeah.
That's the minority. That is the exception.
So we're the rounding error.
Precisely. We are the cosmic dust bunnies. The universe is mostly made of something else entirely, something that refuses to interact with light, refuses to interact with electromagnetism, and yet, without it, we just wouldn't be here.
We wouldn't exist.
Galaxies wouldn't hold together, stars wouldn't have formed, we simply would not exist.
So our mission today is to go on an investigation. We're going to look at how we know it's there if we can't see it. We're going to explore why we haven't found it yet, despite, throwing billions of dollars and the smartest minds on Earth at the problem. And we're going to dig into the radical new theories that are trying to solve the puzzle. Because looking at the research in the last few years, especially the stuff leading up to where we are now in 2026, it really feels like the plot is thickening.
It is.
The old theories are shaking and new contenders are rising.
It really is a fascinating moment in physics. We are arguably at a crossroads. For a long time, we thought we knew what the stuff was, or at least, we had a very confident guess.
A pretty good idea.
A very good idea. But as we will discuss, nature has been surprisingly stubborn. But before we get to the crisis, we have to understand the foundation. We have to understand why we are so convinced this invisible ghost matter exists in the first place.
Right, because it's not like someone just woke up one day and decided to invent invisible matter for fun? This isn't a conspiracy theory.
Not at all.
This goes back nearly a century. We have to talk about Fritz Zwicky.
Fritz Zwicky. You cannot tell this story without him. He was a Swiss astronomer working at Caltech in the 1930s. A brilliant man, undoubtedly, but also a character. He was known for being, let's say, a little difficult.
I read somewhere that he used to call his colleagues spherical bastards. Is that true?
Yes, that is the famous quote. He called them spherical bastards because, in his view, they were bastards no matter which way you looked at them.
That is an incredible insult. Just structurally perfect.
It is, but it gives you a sense of his standing in the community. He was an outlier. And in 1933, he was observing the Coma Cluster.
The Coma Cluster. So what is that?
It's this massive swarm of over 1,000 galaxies, about 300 million light years away. It's a very, very busy place in the universe.
So he's looking at this beehive of galaxies.
Yeah.
And what is he actually measuring? What's he doing?
He's measuring their speed. He's using the Doppler shift of their light to see how fast they are zooming around inside this big cluster. And he's also estimating the mass of the cluster.
How does he do that?
Well, he does it by looking at the brightness of the galaxies. Basically, he counts up the stars, estimates how much a typical star weighs, and then, he does the math.
Simple enough. Brighter means more stars. More stars means more mass.
Exactly. But then he compares the two numbers, and he uses something called the virial theorem.
Okay, let's slow down for a second. The virial theorem. That sounds like jargon. Break that down for us.
Sure. It's actually a beautiful piece of 19th century physics. It basically relates kinetic energy to potential energy.
Motion versus gravity.
Yes. In a stable system, like a cluster of galaxies, there has to be a balance. Gravity wants to pull everything inward. That's the potential energy. The speed of the galaxies wants to fling them outward. That's the kinetic energy.
So gravity is the tether, and speed is the force trying to break that tether.
That's a perfect analogy. If you spin a ball on a string, the string is gravity. If you spin it too fast, the string breaks and the ball flies away. Right. Zwicky looked at the speeds of these galaxies in the Coma Cluster, and they were moving incredibly fast, like thousands of kilometers per second.
So they're really zooming.
They are zooming. And when Zwicky plugged those speeds into the virial theorem, he realized something, shocking. The visible mass, the stars and gas he could see, was nowhere near enough to hold them in.
The string should have snapped.
Ages ago. The cluster should have flown apart and just dissolved into the void.
So the math is telling him that this cluster he's looking at shouldn't exist.
Based on the visible matter, yes. Zwicky calculated that for the Coma Cluster to remain stable at those speeds, there had to be about 400 times more mass than what he could actually see.
400 times?
400 times.
That is not a rounding error. That is not a smudge on the telescope lens.
No.
That is a catastrophe for physics.
It is. And Zwicky, in his typical bold fashion, he published a paper in German. And he coined the term Dunkelmaterie, dark matter.
Dark matter.
He said explicitly that the only explanation is that the vast majority of the universe is made of cold, dark, invisible stuff that provides the extra gravity to keep these things bound together.
And because he was the guy calling everyone spherical bastards, I assume everyone immediately listened to him and gave him a Nobel Prize.
Quite the opposite. They largely ignored him for decades. It was just treated as an anomaly.
A weird data point.
Right. People thought, maybe we're just estimating the mass of stars wrong, or maybe there's a lot of dust we can't see. It was easier to dismiss Zwicky than to rewrite the laws of the universe.
So the idea just sits on the shelf. The ghosts are in the room, but everyone is just pretending not to see them.
For a long time, yeah.
Until the 1970s. Enter Vera Rubin and Kent Ford. And this is where the smoking gun appears, right?
It really is.
Because Zwicky was looking at clusters, these big, chaotic swarms. But Rubin zoomed in. She looked at individual spiral galaxies.
Correct. Vera Rubin was a trailblazer in so many ways, working at the Carnegie Institution. She and Kent Ford developed this incredibly sensitive spectrograph, and they wanted to study the rotation of spiral galaxies, like our own Milky Way or, Andromeda.
And just to set the expectations here,
yeah,
we have a very good model for how things orbit. We live in the solar system. We know how this works.
We do. It's called Keplerian dynamics, named after Johannes Kepler. Just think about our solar system. The sun is in the middle, and it contains 99.8% of the mass.
It's the big one.
It's the bowling ball on the trampoline. Mercury is close to the sun, so it feels a lot of gravity. To stay in orbit and not fall in, it has to move very, very fast.
Right. Mercury just zips around.
Then you go all the way out to Pluto. Pluto is very far away. The sun's gravity is weak out there, so Pluto moves slowly. It creates a curve. Speed is high in the middle, and it drops off as you go out.
So the expectation was, galaxies are just big solar systems. You've got the bright center, that's where all the mass is, and the faint edges where there's less mass. What? So the stars on the edge should be lazy. They should be moving slowly.
Precisely. That was the prediction. Everyone, and I mean everyone, assumed it would be true. But Rubin was the first to actually measure it with high precision. She pointed her spectrograph at the Andromeda Galaxy and others, and she looked at the stars on the very, very outskirts. She found the impossible. The stars on the edge were moving just as fast as the stars near the center.
So the curve, it didn't drop.
It didn't drop. It stayed flat. We call them flat rotation curves.
I love the analogy of the merry-go-round here. I want to make sure I have this visual right. Imagine you're at a playground. You have a merry-go-round. You spin it. If you spin it really, really fast, the kids on the outside edge have to hang on tight.
Right. Centrifugal force.
Now imagine you spin it so fast that the kids should be flung off into the bushes. I mean, by all rights. But they aren't. They're just sitting there, calm as can be, moving at impossible speeds, but they aren't flying away.
That is exactly what Vera Rubin saw. Those stars at the edge of the galaxy were moving so fast that, based on the visible gravity of the galaxy, they should have been ejected into intergalactic space. The galaxy should have shredded itself.
But it didn't.
It didn't. And the only way to explain that, the only way to provide the extra gravitational glue needed to hold those stars in, is if the galaxy is embedded in a massive halo of invisible matter.
A giant sphere of it.
A giant sphere. Rubin showed that the visible spiral, the beautiful glowing pinwheel we see in photos, is just a tiny island in the center of a much, much larger invisible structure.
And this wasn't just one weird galaxy, right? Because skeptics could say, oh, Andromeda is just having a bad day.
No. She did it for dozens of galaxies, then hundreds. It was universal. Every single spiral galaxy she looked at showed this flat rotation curve. The mass required to explain this was typically 5 to 10 times the mass of the visible stars and gas.
So Rubin basically vindicated Zwicky. She proved that this invisible matter wasn't just in messy clusters, it was in our own backyard.
Yeah.
It's the fundamental architecture of every single galaxy.
She did. And frankly, she deserved the Nobel Prize for it, which she essentially never got, which is a whole other conversation about history.
Right.
But scientifically, this was the bedrock. We're in 2026 now, and recent updates using these really advanced spectrographic techniques are mapping these curves with even more precision. We're seeing tiny wiggles and bumps in the data, but the overall conclusion stands firm.
But here is where the skeptic in me pipes up. Okay, so things are spinning too fast. Maybe we just don't understand gravity. Maybe Newton was wrong. Maybe Einstein had a bad day. Is it possible that we are inventing a ghost just to save our math?
That is a very fair question, an excellent question. And if rotation curves were the only evidence we had, you could make a strong case for modifying gravity.
But they're not.
But they aren't. We have the visual proof, gravitational lensing.
This is the stuff that always just blows my mind when I see the photos from the Hubble or the newer telescopes. It looks like something out of science fiction.
It is one of the most elegant predictions of Einstein's general relativity. Einstein told us that gravity isn't just a force, it's a curvature of space-time. Mass tells space how to curve, and space tells matter how to move.
So a massive object is like putting a bowling ball on a mattress. It creates a dip.
Exactly, a great visual. Now imagine light traveling from a very distant galaxy that's behind that bowling ball. The light has to follow the curve of the mattress. It gets bent.
So the massive object acts like a lens, like a magnifying glass or a funhouse mirror.
Yes, a gravitational lens.
Yeah.
And here is the kicker. We can measure exactly how much the light is bent. The amount of bending depends strictly and only on the amount of mass doing the bending. It's a direct scale.
So we look at a cluster of galaxies. We see the background galaxies getting warped and stretched into these weird arcs.
Sometimes even perfect rings of light. We call those Einstein rings.
And we can calculate how much mass must be there to create that much distortion.
And when we do that, we find the exact same things Wiki found. The visible stars and gas are not enough. Not by a long shot. If that's all there was, the light would barely bend at all.
But we see massive distortion.
Massive distortion. It confirms that the cluster is dominated by this invisible mass.
And this allows us to actually map it, right? I've seen these images where they overlay a blue haze on top of galaxy photos. That's the dark matter.
Yes, that is weak lensing. By analyzing millions of tiny, subtle distortions in the shapes of background galaxies, we can reconstruct a 3D map of the mass in the foreground. It's like mapping a glass mountain by looking at how it distorts the trees behind it. We can literally see the dark matter scaffolding.
That is incredible. It's like seeing the wind by watching the leaves move, but on a cosmic scale.
It is.
But we have to talk about the third pillar. Because if rotation curves are the dynamics and lensing is the visual, this next one is the math. The pure hard math. the cosmic microwave background, or CMB.
The baby picture of the universe.
This is the radiation left over from just 380,000 years after the Big Bang.
This is, in my opinion, the most rigorous proof we have. The CMB is a snapshot of the universe when it was a hot, dense plasma. When we look at it with satellites like Planck, we see these tiny temperature fluctuations, hot spots, and cold spots.
And these spots aren't just random noise.
No, absolutely not. They are a pattern, a sound wave, really. The early universe was ringing like a bell. There were these pressure waves moving through the plasma. And just like a bell, the tone of the ring depends on what the bell is made of.
So if you hit a lead bell, it sounds different than if you hit a brass bell.
Exactly. The sound waves were a battle between gravity trying to pull things together and radiation pressure trying to push things apart. Ordinary matter, protons and electrons, interacts with light, so it feels that pressure, it bounces. Dark matter, however, does not interact with light. It doesn't bounce. It just sinks into the gravitational wells.
So it's like the heavy, silent bass line underneath the melody of the regular matter.
That is a beautiful way to put it, a perfect way. By analyzing the power spectrum, which is just the size and intensity of these hot and cold spots, we can mathematically separate the bouncy stuff, which is ordinary matter, from the heavy stuff, which is dark matter.
And what do the numbers tell us?
The numbers are incredibly precise. The data tells us that ordinary matter makes up about 5% of the universe, dark matter is about 27%, and the rest is dark energy, which is a whole other headache for another day.
Another day.
But the point is, if you try to run the simulation of the early universe without dark matter, the picture doesn't match. The acoustic peaks in the data would look completely different. It's an ironclad piece of evidence.
So we have galaxies spinning too fast, light bending too much, and the echo of the Big Bang all telling the exact same story. The universe is mostly ghosts.
The evidence is overwhelming. We know it's there. The ghosts are definitely in the room.
But here is the trillion-dollar question. The question that justifies the billions of dollars in funding for these giant experiments. What are they?
Right.
This is where we get into the identity crisis section of our investigation. Because for a long time, we really thought we had this in the bag. We thought it was WIMPs.
The fallen king, as some might call it today. WIMP stands for Weakly Interacting Massive Particle for, 30 years? This was the favorite. It was the golden child of particle physics.
Why was everyone so sure? What made it so appealing?
Well, because of something called supersymmetry.
Yeah.
Supersymmetry is this really elegant theoretical extension of the standard model, our list of known particles, like electrons and quarks.
Oh, okay.
Supersymmetry predicts that for every known particle, there is a heavier invisible partner, a sparticle, if you will.
A shadow particle for every real particle.
Yes. And the math suggested that the lightest of these shadow particles would be stable, it would be heavy, and it would have been produced in the Big Bang in exactly the right amounts to explain dark matter.
Wait, exactly the right amount.
Exactly. This coincidence was so perfect, so mathematically elegant, that physicists called it the WIMP miracle.
It felt like the puzzle pieces just clicked into place.
It did. It felt like destiny. Nature's usually elegant, and this was pure elegance on paper.
So we built detectors. Massive ones, from what I understand.
Yeah, we did. We dug deep holes in the ground. I'm talking about the LUX experiment in South Dakota, Super CDMS, and the giant xenon detectors in Italy. These are cathedral-sized experiments buried under mountains.
Why under mountains? What's the point of that?
To block the noise. The surface of the Earth is constantly bombarded by cosmic rays, all sorts of radiation from space. If you put a sensitive detector on the surface, it would just light up like a Christmas tree.
So you'd never see the signal.
You'd never see the faint whisper of a WIMP. So we go deep underground into old gold mines, into tunnels under the Gran Sasso Mountains in Italy to use a kilometer of solid rock as a shield.
And the detector itself. What does it look like inside that cavern?
The best ones today are these big vats of incredibly pure liquid xenon. Xenon is very heavy and dense. The idea is that billions of WIMPs from the galaxy's halo are passing through the Earth, through you, and through the detector every single second. Most of them pass right through the spaces between the atoms. But statistically, every once in a while, a WIMP should crash head-on into a xenon nucleus.
Like a tiny, invisible billiard ball collision.
Right. And that collision would create a tiny flash of light and a release of charge. We've lined the tanks with these photomultiplier tubes, basically super sensitive digital eyes, just waiting and waiting for that flash.
What have we found?
Nothing. Absolute silence. So we have run these experiments for decades. We have made them bigger, more sensitive, quieter. We have ruled out vast swaths of the parameter space, that's the range of possible masses and interaction strengths, where the WIMP could be hiding.
The WIMP miracle is turning into the WIMP nightmare.
That's a very good way to put it.
I can imagine that physicists are getting a little nervous.
Nervous is putting it mildly. There is genuine anxiety in the field. People have built entire careers on supersymmetry and WIMPs. If WIMPs don't exist, it's not just a missing particle. It implies that our fundamental theory of how to extend physics beyond the standard model might be completely wrong.
And we are hitting a physical wall soon, aren't we? I was reading about something called the neutrino fog.
Yes, this is the ultimate limit. As our detectors get more and more sensitive, trying to find that incredibly faint WIMP signal, we start seeing something else. Neutrinos.
The other ghost particle. The one we know exists.
Right. Neutrinos come from the sun, from cosmic rays hitting the atmosphere. They are everywhere. Until now, our detectors weren't sensitive enough to see them as background noise. But the next generation of detectors, like the upcoming Darwin experiment, will be so sensitive that they will start detecting neutrinos constantly.
So the background noise becomes as loud as the signal you're looking for.
Exactly. It creates a fog. Once we hit that neutrino floor, we can't distinguish a WIMP from a neutrino anymore. If we haven't found WIMPs by the time we hit the fog, we likely never will with this technology.
That is incredibly high stakes. We have maybe 5 or 10 years left to find the WIMP, or the theory is effectively dead in the water.
Effectively, yes. That's the feeling in the community.
Okay. So if the king is falling, who is the rising star? The new pretender to the throne. I keep hearing about axions.
Axions are the new darling of the physics world. And what's so interesting is they were originally proposed to solve a completely different problem in quantum physics called the strong CP problem, which involves why the neutron doesn't have an electric dipole moment.
I'm going to pretend I understood that. But let's focus on the dark matter part. How are they different from WIMPs?
They are polar opposites. WIMPs are heavy, big, brooding linebackers. Axions are incredibly, incredibly light. We're talking billions of times lighter than an electron. They are so light that, according to quantum mechanics, they stop acting like individual particles and start acting like a coherent wave.
So a ghost wave just washing through the entire galaxy?
Exactly, a sea of axions. And because they are so light, they don't crash into xenon atoms. You can't catch them in a tank like a WIMP.
So how on earth do you catch them?
You use a very clever trick called the Primakov effect.
The Primakov effect.
The theory predicts that if an axion passes through a very strong magnetic field, it has a tiny chance to spontaneously convert into a photon, a particle of light.
Wait, the dark matter turns into light?
Under the right conditions, yes. Specifically, a radio wave or a microwave. So the experiment isn't a tank of liquid, it's a radio.
A radio.
Experiments like ADMX, the Axion dark matter experiment, are basically giant, supercooled magnetic cavities with an antenna inside. A very fancy thermos with a magnet.
And they are just listening.
They are listening for a very faint hum, a specific frequency that corresponds to the mass of the axion. But here's the problem. We don't know the mass, which means we don't know the frequency.
It's like trying to find a specific pirate radio station on an infinite dial, but you don't know the number.
And you have to listen to each frequency for days, sometimes weeks, to be sure there's no signal there before you move the dial a tiny, tiny bit. It is a slow, painstaking process of tuning the dial.
But there's a lot of hype there, a lot of excitement.
There is. As WIMPs fade, the theoretical motivation for axions is looking stronger and stronger. There have been some intriguing excesses in the data, little blips that might be something, but nothing confirmed yet. Still very exciting.
Are there other suspects? I mean, the universe is a big place. It can't just be these two.
Oh, there are a few others. There is the ghost sterile neutrinos. These would be heavier cousins of the regular neutrinos we know that interact only via gravity. Nothing else.
Even less interactive than normal neutrinos.
Far less. They could explain some weird anomalies we see in neutrino oscillation experiments, but the evidence is very messy, statistically weak.
And what about black holes? I mean, they're dark, they have mass. Couldn't the universe just be full of black holes we can't see?
This is the heavyweight contender, primordial black holes, or PBHs.
How are these different from the regular black holes we hear about?
Regular black holes form when a massive star dies and collapses under its own gravity. Primordial black holes would have formed in the first fraction of a second after the Big Bang. The universe was so dense that little pockets of matter could have just collapsed directly into black holes without ever needing to be a star first.
And this idea got a big boost recently because of LIGO, right? The gravitational wave observatory.
Yes. Since 2015, LIGO has been hearing black holes colliding all over the universe. We hear the chirp of their merger as a gravitational wave, and some of them are surprisingly big, like 30, 50, even 80 times the mass of our sun. That mass range is actually kind of hard to explain with normal stellar evolution.
So some theorists thought, hey, maybe these are the ancient ones, the primordial ones. Maybe these are the dark matter.
It's a very compelling idea because it doesn't require any new particles. It just requires gravity, which we know works.
So why isn't this the leading theory?
Well, there are constraints. If all the dark matter were made of these black holes, they would act like little lenses all over the sky. We would see stars and other galaxies flickering as these black holes passed in front of them. We've looked for that. It's called microlensing, and we just don't see enough of it.
So they can't be all of the dark matter.
Probably not. But could they be 10% or 20%? Absolutely. It's entirely possible that dark matter isn't just one thing. It could be a cocktail, a bit of axions, a sprinkle of primordial black holes.
Okay, so we have our lineup of suspects. We have the heavy WIMPs, the wave-like axions, and the ancient black holes. But we have to address the elephant in the room, the skeptics. What if there is no suspect? What if the ghosts aren't there at all and we're just seeing things wrong? What if our understanding of gravity is fundamentally broken?
This brings us to Mond-modified Newtonian dynamics. This is the scientific insurgency.
The rebels.
The rebels, exactly. The premise is actually quite simple. Maybe there is no invisible matter. Maybe gravity just works differently than Newton and Einstein said.
How so? In what way?
MOND suggests that at very low accelerations, like what a star feels drifting at the very edge of a galaxy where gravity is incredibly weak, the force doesn't fade away as quickly as the inverse square law predicts. It stays stronger for longer.
So gravity gets a boost at the edges of galaxies.
Exactly. And here is the frustrating or, fascinating thing about it. MOND works.
It works.
For galaxy rotation curves, it works shockingly well. You can take a galaxy, look at its visible matter, apply the MOND formula, and predict the rotation curve almost perfectly.
Better than dark matter models.
Sometimes, yes. Because dark matter models have to make assumptions about the shape and size of the invisible halo, which gives them some wiggle room. MOND has no wiggle room. It makes a direct prediction, and it often nails it.
So, why aren't we all MND believers? Why are we still hunting for particles underground?
Because MOND falls apart on the big stuff. When you try to apply MOND to the cosmic microwave background, the math just fails. It can't explain those acoustic peaks we talked about earlier.
I see.
When you look at galaxy clusters, MOND doesn't provide enough gravity to hold them together either. You still need to add some unseen matter, like neutrinos or something, to make it work.
So MOND fixes the galaxy problem, but it breaks the universe problem.
Exactly. It's like fixing a leak in the roof, but causing the basement to flood. Most physicists prefer dark matter because it works on all scales, from the early universe to clusters to galaxies. But MOND refuses to die because it is so darn good at that one specific thing, galaxy rotation.
Let's talk about how we are looking right now in 2026. We mentioned the underground tanks for WIMPs and the radio tuners for axions. Is there any other way to spot this stuff?
There is. There's the space approach. Indirect detection. This relies on the idea that dark matter particles might be their own antiparticles.
Meaning if two of them crash into each other.
They annihilate. Poof. They turn into pure energy, specifically high-energy gamma rays.
So we look for a gamma ray glow from places where dark matter should be dense.
We look right at the center of our galaxy where the dark matter density should be the highest. And interestingly, the Fermi Space Telescope did see a glow. It's called the Fermi excess. For years, we've seen an unexplained surplus of gamma rays coming from the galactic center.
Could it be dark matter?
We thought so for a while. It's very exciting. But more recent analysis suggests it might just be a large population of millisecond pulsars-old spinning neutron stars that are too faint to see individually, but together create a kind of diffuse glow.
So a more boring explanation.
It's never easy, is it?
No.
The universe is a messy place. It's very hard to tell the difference between a groundbreaking dark matter annihilation signal and a bunch of old stars just doing their thing.
Okay, let's move to some new mysteries. Because just when we thought we understood the problem, the universe threw us a few curveballs. The plot, as they say, thickens. Let's talk about the full tension.
This is the biggest crisis in cosmology right now. It's a fundamental discrepancy in the expansion rate of the universe.
So how fast is the universe growing?
Exactly. We have two very good ways to measure it. One is the early universe method. We look at the CMB, our baby picture, and project forward using our standard model of dark matter and dark energy. That gives us a speed of about 67 kilometers per second per megaparsec.
Okay, 67. Got it.
The other way is the late universe method. We look at stars and supernovae nearby and measure how fast they're moving away from us right now. That gives us a speed of about 73.
67 versus 73, they don't match.
They don't match, and the error bars don't overlap. Both measurements are incredibly precise, and they fundamentally disagree. This suggests our standard model of the universe is missing a piece.
And how does this connect to dark matter?
It might. Some theorists have proposed ideas like early dark energy or perhaps decaying dark matter to solve this.
Decaying dark matter.
Yeah, what if dark matter isn't perfectly stable? What if a small fraction of it decayed into other particles over billions of years? That could change the expansion rate and bridge the gap between 67 and 73.
So the dark matter might not be a permanent ghost, it might be a fading ghost.
It opens up the possibility of a dark sector that is dynamic and evolving, not just static and boring.
But here's the development that really caught my eye. This feels like a Sherlock Holmes moment. Ultra-diffuse galaxies. UDGs.
The ghost galaxies.
Yes.
Could you describe them for us? What are they? These are strange beasts. They are the size of the Milky Way, so huge, but they have 100 to 1,000 times fewer stars. They are incredibly faint and spread out. You can look right through them.
And usually, these things are held together by a ton of dark matter, right? That's the only way to keep those few stars from just drifting away.
Correct. Most UDGs we find are 99% dark matter. They are basically big, fluffy balls of dark matter with a light sprinkling of stars. But recently, specifically with two galaxies named NGC 1052 DF2 and DF4, scientists found something that shouldn't exist. They found galaxies with almost no dark matter.
Wait, a galaxy with no dark matter? I thought we needed dark matter to hold galaxies together. How is that possible?
That's the puzzle. But here's why this is so important for the skeptics versus the believers. This discovery is the smoking gun against MOND.
Walk me through that logic. Why is this bad for MOND?
Okay. If dark matter was just an illusion of modified gravity, if MOND was right, then gravity is a law of nature. It should apply everywhere, to every galaxy in the same way. You can't just turn a law of physics off for one galaxy.
Right. Gravity's gravity. It shouldn't care which galaxy it's in.
Exactly. But if dark matter is a substance, if it's stuff, a fluid, a particle, then it can be separated from the stars. Maybe during a collision between two larger galaxies, the gas got stuck together to form stars, and the dark matter kept going. Maybe tidal forces from a neighbor stripped the dark matter away.
So finding a galaxy without dark matter actually proves dark matter is a real thing, because it proves you can separate the two ingredients.
Bingo. It proves they are distinct components. It's like you can have coffee without cream. If cream was just an inherent property of coffee, you couldn't remove it. Finding a dark matter-free galaxy is one of the strongest proofs we have that dark matter is a physical substance.
That is deeply ironic. The absence of it proves its existence.
Science is full of such ironies. These galaxies are a complete nightmare for modified gravity theories, but a fascinating new puzzle for our dark matter simulations.
So, looking ahead, what is the future landscape? We're here in 2026. What's coming down the pipe that could finally crack this?
We are entering what I would call the golden era of observation. We have the Euclid satellite, which launched back in 2023. It is currently in the process of mapping billions of galaxies to check the large-scale scaffold of dark matter across the entire sky. The data pouring in from Euclid is going to be transformative. It will tell us if the lumpiness of the universe matches our dark matter models.
And the Vera Rubin Observatory on the ground.
That is the big one. That's the game changer on the ground in Chile. It's coming online very soon, and it will survey the entire southern sky every few nights. It's going to make a movie of the universe.
A movie?
A decade-long movie. It will find millions of new objects, and, crucially, it will test dark matter theories by looking for substructure.
Substructure, what's that?
Small clumps. If dark matter is cold, like slow-moving WIMPs, our simulations predict there should be lots of tiny, small clumps of dark matter floating around big galaxies like ours. If dark matter is warm, made of faster-moving particles, those little clumps get smoothed out. Vera Rubin will be able to see the subtle effects of these clumps by how they disrupt streams of stars.
And what about on the theory side? Are we shifting our mindset?
Yes, big time. We are moving away from the simplistic idea of it's one particle. We are starting to think much more seriously about a dark sector.
A dark sector?
Maybe there are dark atoms, dark forces, dark photons that only dark particles can feel. Maybe the dark universe is just as complex and rich as the visible universe we know.
That's a humbling thought. We have the whole periodic table of elements for our stuff. Oxygen, carbon, iron, all of it. Maybe there's a whole periodic table of dark stuff that we know absolutely nothing about.
It is entirely possible. We might be looking for a single proton when there's actually a whole dark chemistry out there.
So bring it all home. We started this journey with a paradox, the invisible universe. We looked at the history from Zwicky's crazy hunch to Rubin's meticulous rotation curves. We looked at the evidence lensing, the CMB, the structure of the cosmos. It's undeniable that something is there.
Absolutely. The evidence is robust. But the identity remains completely elusive. WIMPs are hiding well, perhaps too well. Axions are looking good as the new favorite. And modified gravity theories are still lurking in the background, just waiting for us to fail at finding a particle.
It really feels like we are on the brink of something big, one way or another.
We are. The search isn't just about finding a new particle to add to the textbook. It's about understanding the fundamental architecture of reality. We are realizing that the stuff made of protons, neutrons, electrons, we are the anomaly. We are the cosmic dust bunny in a room full of invisible giants.
And I want to leave the listener with a final provocative thought. Something I was thinking about when you mentioned those ultra-diffuse galaxies. The ones with stars, but no dark matter.
Go on.
If dark matter is a substance, and it's 85% of all the matter in the universe, and we now know you can separate it from stars.
I see where you were going with this.
Doesn't that mean there should be galaxies out there made entirely of dark matter? Vast, invisible structures rotating and drifting through the void with no stars at all to light them up.
It is a statistical certainty. Our theories predict that dark galaxies should exist. Massive halos that, for whatever reason, never managed to catch enough gas to ignite star formation. They would be completely invisible to our telescopes, detectable only by their gravity, maybe if they passed in front of something else.
There could be one right next door to the Milky Way, 100 times bigger than us.
We might be drifting through one right now and never, ever know.
A haunting, beautiful thought. On that note, thank you for joining us on this investigation into the invisible.
It was a pleasure.
Keep looking up and keep wondering what else is out there that you can't see.
Stay curious.